We will continue with cloud architecture, basically a software architecture for cloud. So let's look at another important design pattern, architecture pattern rather, which have emerged recently, which is called microservices. Microservices is essentially revisit of service-oriented architecture, specifically meant for highly distributed cloud-based systems. Let's look at microservices, how it is implemented, and various design patterns related to this. So for this microservices, essentially we have taken the content from various websites, primarily from Martin Fowler's website, and there is a book called Release It. So the content is taken from there because it's still quite new. This topic is quite recent, and we don't really have textbooks describing this microservices. So microservices is essentially an approach to develop applications as a collection of small components or modules. It is essentially in a sense a modular design. Now, modular design is not a new concept. It is there since 1970s, but modular design gets a whole new meaning in the context of cloud-based systems. So it was right from the beginning when people proposed modular design. One of the important tenet of module-based design is that each module is relatively independent in terms of its functionality, and different modules interact with each other to accomplish the overall functionality. So in microservices, basically this modular design pattern has been followed in spirit. So what is proposed here is that each module is essentially independently compilable and independently deployable, independently replaceable and upgradable. So these are the additional features that are considered, that here each module, each component is not just independently deployable, but they are also independently replaceable. I can replace this with another one, or I can upgrade it, and therefore inter-module interaction is highly loosely coupled. So the old principle of loose coupling and high cohesion is very strictly followed here. So what is basically a microservice? Basically a microservice is nothing but it's a collection of components that provide a business functionality, and microservice basically uses the principle of published interface, and it is out of process. It basically runs in its own process. Each microservice runs in its own process, and they communicate with each other using REST style communication. That's an important feature, that microservice basically is a small, relatively complete unit, business unit. Sorry, it's not a business. It basically it's a small unit that accomplishes a business functionality, and they interact with each other using the REST protocol. Let's look at some of the examples later on. So an application essentially is a collection of such microservices, where each service can be at least one process, or it can span across multiple processes. Now, another important part of microservices is that each microservice potentially can use their own database. So there is no concept of common database which is used by all the services. It is basically the database is split and distributed across different services, and application, as I said, is a collection of such microservices. Each service can be implemented using different languages. Like one module can be in C, another module can be in Perl, another module can be in Java. That's perfectly valid, and that's possible because, as I said, these modules are actually quite independent and they interact with each other through REST protocol. So therefore it is not necessary that you have to use only one technology for all the components. Therefore in this case there is very little centralized management, unlike a traditional application. In the context of microservices, the proponents of microservices pattern describe something called or termed a particular phrase called monolith. So the proponents of microservices said that the opposite of microservices is essentially a monolith. So let's understand what is basically a monolith. So monolith does not mean a monolithic application that were traditionally built during mainframe days. So those were of course monolithic applications, one single application having a bunch of files. I'm not talking about that kind of monolithic application. I'm talking about even the popular commonly used applications, web-based applications. In fact, they are also called monolith according to the microservice people. So let's understand what is monolith versus what is microservices here. So in monolith, what is and you can see that picture on your left. So this is a typical web-based application, and this is called monolith because here these three modules like banking front end, account management module, money transfer module, they're all kind of combined together to form one application. Let us say this is a J2EE application. Then these three modules could be Java beans, EJBs essentially. So they are all deployed on a given application server, and they all interact with RDBMS, and the web server is load balanced. So this is how this application will run, and this is basically a very common example. This is how many such web-based application has been built so far. This is called monolith, and we will see why. Now, according to the new definition of monolith, a monolithic application essentially puts all its functionality into a single process. Of course, that process can have multiple threads, like J2EE application server can be multi-threaded. There could be each of these functionality can be executed on different threads, but the point is that there is one single process in which a monolithic application is running. So how does this monolithic application scale? It scales by replicating the monolith process onto multiple servers. So let's look at the picture in the middle, this particular picture here. Okay, these shapes, like this diamond shape or this triangle shapes and so on, these shapes, each of them basically denotes a kind of a service or a functionality. So this is one functionality, this is another functionality, this is another functionality, this is another functionality, and this is another function. So there are 5 functionalities. Like this is one functionality, this is another, so on. Now these are all combined into one single process, and scaling is done like this. The whole thing, this whole process is replicated in 4 times into 4 different machines. and even the database is also replicated. Same data is copied in multiple machines, multiple nodes, and traditional availability techniques like hot swap, cold swap, or warm swap, those techniques are applied here, meaning that maybe at any given point in time one of them is active, but others are also kept in a standby mode. If one fails, the other can take over, or even they can be used for load balancing. For example, the load balance to www server might send some request here, some request here, some request here, and some request here. So that's how maybe the scalability is achieved. But still, this is called monolith because all these functionalities are combined together into one process. Now look at the microservices based architecture on the right here. So what happens is that each such functionality, like this one or this one or even this one or even this one, these are, instead of combining together into a single process, each of them are running in a separate process. Like this is one process, this is another process, this is another process, and this is another process. There are 4 processes running. Each process is implementing only one service, and they are interacting with each other through REST protocols. And now scaling happens exactly the way the scaling happened here. So this whole thing is replicated 4 times. So also notice a few things here. Here, for example, this particular service is replicated twice here. So there is a redundant copy of the same service running. In this particular case, in here, there is no redundant copy. All of them have single copy. Here you see that there is another copy of this running. Here you see that, for example, 2 copies are running here. In fact, if you just count, there are 1, 2, 3, 4 copies of the same service which are running across 4 machines. Similarly, 3 copies of this service is running. Similarly, 5 copies, 1, 2, 3, 4, 5 copies are running in four machines. So the distribution of services are across different servers. This picture indicates that unlike in the monolithic case, first of all, the services are distributed and they are scaled across multiple machines. Also note that the database, which was also monolithic here, this is a data item, this is another data item, this is another data item. They are all combined into possibly one database, maybe multiple tables, but one database. In this case, these are all separate databases. So these separate databases running on separate machines, separate nodes, and there is an aggregator which might be used to aggregate data from all of them, and that aggregator supplies the data to these microservices. So that's the basic design of microservices versus monolith. So here the basic design principle is that it consciously avoids a very famous law in software engineering called Conway's law. So Conway's law says that design of a system is essentially a copy of the organization's communication structure. So what that means is that if there are a group of people who are physically close, they tend to form, and if they are supposed to work in a team, or rather they are supposed to work in a big project, then the people who are physically close, they form a team and they basically also create a module. So the modular structure of a big system basically represents the physical closeness of the developers. If there are 3 modules in a system, then according to Conway's law, most likely there will be 3 groups who have developed these 3 modules. Now this is basically avoided here. Here the whole idea is that create a service that is based on a business functionality with its own user interface, own business logic, as well as its own database. So another principle is that use smart endpoint but use a dumb pipe, meaning that pipe means the communication mechanism. So idea is that do not rely on the intelligence of the pipe. Basically, pipe should be just a dumb, simple communication protocol. Just transfer the data in a very simple manner. So what is then a not so what is a non-dumb pipe? So what kind of pipe could be non-dumb? Well, what they mean is that don't use, for example, SOAP protocol. SOAP is essentially much more rich communication protocol, and therefore it is quite heavy. So if the pipe is dumb, for example, like REST protocol, then it is lightweight, and then you can achieve scalability. You can basically have very fast communication. Here the whole idea is that split functionality into services, make each service smart and complete, and make sure that the interaction between services are really lightweight, which is why it is called dumb pipe. So one standard architecture pattern is pipe and filter. So microservice can actually use pipe and filter model, where the service is a filter. All it does is it receives a request, processes the request, and then produces a response. So it suggests that use a REST protocol, not complex BPEL or SOAP. Data management is decentralized, and most importantly, this whole microservice is designed for failure, meaning that it is fault tolerant. And we will see some of the important design patterns. So let's look at the data storage. The data storage here is instead of a monolithic database, there are, in the microservice based database, the entities are split. Of course, logical entities. I mean, you don't really split really fine-grained entities, but you split more coarse-grained entities into separate databases. Obviously, on the main entity and its helper entities are grouped together to form one database. And likewise, here it is another split, here it is another split. However, in the monolithic case, they are all put in the same database there. So because the data is also split, there one could use multiple types of data store, not necessarily relational here. So the disadvantage is that the moment you use multiple technology, it creates an integration problem. It's a new interface that need to be considered, and this will also increase the consistency and availability problem. But it is definitely faster, specifically when the application demands that the response time should be fast. The relational database may not be the right choice. In that case, one can basically use a mix and match. The typical design flaws, for example, application was essentially composing and serving web pages. In that case, they basically looked up the page elements by the IDs. Now, these design flaws are with respect to a relational database. What I'm trying to say is that in a typical web-based application, oftentimes the functionality requires that an application creates or serve multiple web pages, and essentially the page elements are searched by IDs, and that's it. So in that case, it's not really necessary to create a complex join or complex analytics queries. So in such a case, you don't really need a strict transaction, or there's no need to share databases. In fact, it would be a much better idea to use a key value store to basically implement such functionality of serving multiple web pages, composing web pages, look up page elements by ID. In all these cases, a key value store is a far better choice than a relational database. So microservices design pattern, which is extended to data persistence, would actually help addressing this. Example is that the Guardian website basically has been rebuilt using MongoDB recently. Let's look at how you can implement a microservice. So let us assume that you have built a banking application, and there are two services, money transfer service and account management service. The account management service essentially stores different accounts, manages accounts, creates account, deletes account, and maintains the balance. And the money transfer module or money transfer service transfers money from one account to another. Simple application. So one money transfer request would look like this, that from account ID 101 to account ID 202, amount 55 should be transferred. So the way microservices based application would work is like this. Basically, microservices based applications will heavily use event based communication as opposed to typical transactions. In a typical database kind of transaction, you will create a transaction where you will debit 55 from account 101 and you will credit 55 to account 202. Instead of that, here what happens is you create a series of messages. First of all, this money transfer service publishes two events. One is money transfer event, and another is debit completed event. And account management service essentially subscribes to those events, money transfer event and debit completed event. So money transfer event, money transfer service will publish these two events, which will be subscribed by account management, and then once account management service is notified about money transfer or debit completed, it will take the necessary action. Similarly, account management service will also publish events like account debited or account credited. So when an account is debited or account is credited, it will publish those events. And money transfer service will subscribe to these events like account debited event and account credited events. So by subscribing these events, these two services will accomplish their tasks. Now, how will this transaction be made consistent? To maintain consistency, a microservice should automatically publish an event, and those messages would be stored in a database, and then they will be updated. As soon as a new entity state or event is created, an event can be marked as consumed or complete, and they actually use something called eventually consistent mechanism. We will learn about eventually consistent mechanism later on, which is one of the major design consideration for cloud-based systems. So in order to implement eventually consistent mechanism, what microservices does is it replaces events to recreate the state, and it is no longer a two-phase commit protocol. This is certainly much more difficult to implement because it's not that straightforward. Here, a simple debit and credit of accounts can result in so many, at least 4 to 6 events which are to be published and consumed. That's certainly difficult to implement. So this account service will have balance, and then we'll have this open debit and credit. Now, the traditional method of maintaining an account table is not the way one should do. So here you are not going to basically lock this table and then do a debit and credit here. That's not the way microservices based data access, data update is going to happen. It's going to happen completely based on the event table. So the design will basically create a set of event and event tables. So essentially these event tables will have event IDs, and then this is account ID, and then the action, and then the amount. So here for account 101, there is account is opened with 500 rupees. Here this account is credited with 250 rupees. Here the account is debited with 300 rupees, and so on. And these event tables are basically consulted, and then the final account table is updated. So what I want to repeat is that this style of programming, this style of data management is very different from traditional relational database. So we will also understand the architecture to handle the failure. Services can actually fail at any point in time. It is important to be able to detect such failures very quickly, and if possible one needs to automatically restore the service. That's the main point in microservices. That's the reason why microservices are talking about having small but complete service. The whole purpose is that one should be able to really fail quickly, and then detect and fail quickly, and then immediately restore. A microservices based application therefore puts a lot of emphasis in designing real-time monitoring to check things like architectural elements, like for example how many requests per second is there on a given database, how many requests are being processed by a given service, etc. And there are business relevant metrics are also there for monitoring purpose. For example, it can basically monitor how many orders are getting processed in a given minute. There could be semantic monitoring, for example, and that can provide an early warning system if something is going to be wrong. It can trigger development teams to follow up and investigate if there is any anomalous situation appearing. This is particularly important to hear because application consists of a set of microservices collaborating with each other through messages and events. So therefore it is far more complex compared to, as I said, a traditional system. Therefore it is highly important that as an architect you build a monitoring system essentially that keeps track of these events that are getting published, and by not just keep track but also analyze those events in sequence to find out whether there is any anomaly which can cause a failure later on, and basically create an early warning. Let's look at in this context different fault tolerant architecture patterns which are typically used in microservices. In a service-oriented designs, integration with external systems is essential, and that's very much true in microservices as well. Now, many a times the failure reason is due to the problem with the external system. Failure can take several forms, ranging from network errors to semantic errors, and error responses will be difficult to decipher. Errors can be protocol violation, slow response, or even outright hang. So fault tolerant programming, one of the well-known design pattern is called circuit breaker pattern or timeout pattern, that will help in avoiding something called a cascading failure. It can also reduce the risk of a denial of service attack on your service. So let's look at the circuit breaker pattern. So the circuit breaker pattern looks like this. Here there is it's basically a state transition diagram. So the circuit is essentially closed, and this is implemented for a given service, which is important. So on call, meaning that if someone calls for a service, then when it is in a closed state, the call is passed through, and then a success count is incremented. In fact, when this call is successful, then the count there is some count, failure count actually, that count is made to 0. So the idea is that if someone makes a call to a service, it is allowed to pass through, and then the return of the particular service is monitored, and if the service has returned successfully, then the count is kept to 0. Otherwise, if the call fails, then this failure count is incremented. In fact, when the failure count when it failed, the count is not just incremented, it goes to another state which is called an open state. So when it goes to an open state, then if an external agent again makes a call to the service, it immediately fails and essentially notifies the client that the service is not available, and internally it starts a timer. So the purpose of the timer is that it expects that when a failure happened, the design team or the operational team is looking into it and trying to fix this. So there is some timeout. So after the timeout, then the system goes to a half open state. Here basically when there is a call, this call is allowed to pass through, and it is monitored whether the call is successful or not. If it is successful, then it goes to a closed state, meaning that the fault is repaired. However, if the call fails, then it assumes that the service is still not up, so it again goes to a failed state, and in fact it goes to an open state again. So it goes to open state here. So this is what I said, the critical call. So this must be implemented for only critical services, not for every service, because this circuit breaker is a wrapper on top of the main service. It is not that, it is actually a complicated design pattern. It's not that easy to implement. So this wrapper essentially wraps the main service, and it remains in the closed state, as I said. If the call is successful, then nothing extraordinary happens. If it fails, then the circuit breaker makes a note of the failure, and then it goes to basically open state. Sometimes one can build a frequency of failure now, or it has a count of failure. In fact, if the failure count exceeds a certain threshold, in that case it can go to open state instead of just one failure. That's a variation. After some time, the state is reset and to closed, thinking that the problem is actually fixed. So this is a well-known pattern called, so this circuit breaker pattern essentially handles this kind of failures, and then essentially ensures that there is no cascading failure. So there will be a quick question to the listeners of this particular course. So if you are to implement this circuit breaker, can you think of a design pattern that can help in implementing this circuit breaker? Let's look at another pattern called bulkhead. So bulkhead is essentially about splitting the functionality. So in this case, this foo and bar are two services. They use another service called buzz. So foo and bar are basically two microservices. They depend on the common service called buzz, and if foo crashes or consumes excessive resource, or it is compromised, security attack, then or it can even trigger a bug in the buzz, then bar will also suffer. So therefore the idea is to partition buzz. So here buzz is partitioned into two, one for foo, another for bar. If foo, bar and buzz use the same resource pools, and if the resource demands are known, then a shared pool can be much more cost effective. One can use a VMs for load balancing and implementing this kind of pattern. So essentially you can have one VM implementing the buzz for foo, another VM for the bar. and that's how the capacity can be planned. And in fact, one can ensure that if foo is compromised or foo is consuming too much of resource, it is restricted to one VM, and that's not going to really impact the bar. So again, the question is that we have already talked about bulkhead just a few slides back in the context of microservices. So you can recall or you can refer back to those slides and those lectures and try to see that how this bulkhead was actually implemented and in what part of microservices. So before going to timeout, maybe I will answer the question of bulkhead. So essentially, if you look at the microservices architecture, one important point was that you split the database into multiple logical entities, and that splitting of a database is essentially the idea of bulkhead. Let's look at the timeout pattern now. Timeout is basically a simple mechanism to break from waiting for an answer beyond certain point, typically external calls, network calls, that when that exceeds a threshold, then essentially this needs to be broken. Asynchronous call mechanism is another way, but it is too complex to implement in a particular situation. Timeout is a much simpler mechanism. So well-placed timeouts essentially can provide a nice fault isolation. Today, in whatever APIs that we use, the program level APIs that we use, unfortunately they don't really implement such timeout patterns. Therefore, and there is no way you can essentially implement such timeout patterns. Vendor provided client libraries are also devoid of such timeouts. These libraries basically hide socket communication mechanism and basically prevent setting timeouts. Oftentimes a client library might be implemented which is using socket programming, but it does not take care of the situation that if the communication is lost, instead of waiting forever, it should break immediately. Timeouts are relevant within a single application, specifically in a multi-threaded application. So question to you again is that suppose you are to implement a timeout based system, and you already have an API, you already have a library which basically uses such external communication mechanism, and it has not implemented the timeout. Then how would you introduce timeout? How would you add this additional feature of timeout on top of a given functionality? Can you think of a design pattern which can help you in adding this timeout feature? Microservices is linked to scalable deployment, and scalable deployment is essentially people talk about three-dimensional deployment. So let's look at this three-dimensional deployment in more detail. So in this particular cube diagram, this point, which is 0, 0, 0, this essentially is a monolithic single system, and this monolithic single system is essentially catering to all the customers, let us say customers ranging from A to Z. Now let us look at the scaling across the x-axis. So scaling in x-axis means that a set of redundant load balanced clones. So if you are to just clone this monolithic server along this, then it means that you just clone this data into a load balanced set of servers. That's basically scaling of the monolithic system across x direction. If you are to essentially scale across y direction, then you partition the services across along the functionalities. So instead of having all the functionalities, all the features grouped into a single process, you split them into multiple processes like login, browse, checkout, etc. These are all separate processes, and that's how you do a scale here, so by partitioning the service. The z-axis is essentially partitioning the data. So here what's happening is that the data for customer A to F is into one database, data for F to R is into one database, and data for client S to Z would be in another database. This is just an example. The partitioning can be achieved in any other way. Remember, this is again the bulkhead design pattern. So this point is monolithic and this point would be a microservice. Here you are achieving essentially a scaling in both X, Y and Z direction. That's what would be a good scalable deployment for a microservices based system. Let's look at this picture again. This account management service, there is a money transfer service, and there is event based communication through a message bus. Account management service would be managing its own account database, whereas money transfer service would maintain its own database, which will just keep track of transactions. And this is how these two databases are actually separated. This is an example of a bulkhead. This is also an example of a bulkhead.